Let's proceed with analyzing systems, equilibrium systems of salts of limited solubility in water. Materials which students of chemistry often refer to as precipitates. Have you recognized now in 46 laboratory that a common way to test for the presence or absence, as the case might be, of an ion in solution is to see if you can get that ion to react with another ion to make a precipitate? You've been doing this in 46L? You find out that K plus can be precipitated by reaction with cobalty nitrite ion, a rather fancy complex ion. You did that in assignment 2. Ammonium ion also does that. Upshot for assignment 246L. If sodium ion's in the sample, you will get a distinct, intense, long-lasting, yellow to yellow-orange flame test, right? Which eliminates the possibility of testing for potassium ion's presence by flame analysis, because the intense sodium ion flame masks the potassium ion flame. And if the sample also contains ammonium ion, which reacts with cobalty nitrite to give an orangish crystalline precipitate, which is deeper in color than the yellow-orange precipitate of cobalty nitrite that you get with potassium ion, means that if you analyze an unknown sample and you find out that sodium ion is present by flame analysis, which is the only test we use for sodium ion because it gives the most distinct, intense flame result, and the sample contains ammonium ion, you got a problem testing for the presence of potassium ion, don't you? Because the only remaining test is the precipitation test, and ammonium ion is standing in the way of using the precipitation test for potassium ion by cobalty nitrite in a reliable fashion. Because the ammonium ion also reacts with cobalty nitrite to give a precipitate, a deeper orange colored precipitate. So what do you have to do if you face this dilemma to test successfully for K+? What do you learn about in assignment 2? What do you have to do? You have to get rid of ammonium ion. So you're looking at this solution, if you're dealing with a solution. You're staring at it intensely. Solution! Do you or do you not have K+? And K+, like all good ions, remains totally mute. Says to you, nothing. So you have to do some chemistry to find out, don't you? What do? You got a solution. It's got sodium ion in it and ammonium ion in it. What do you do to find out if this solution's got a K+ in it? And when students come to me, when I teach 46L, students come to me to get their scheme of analysis approved, to get permission to do the 2AB analysis. I want to find out if they're going to do this analysis successfully. That's one of the questions I ask them. If they can't answer that question successfully, I say, sorry, scheme not approved, go away. No permission to do 2AB. Permission denied. Till you can answer that question successfully, amongst other questions I'll ask you, to convince me you know the chemistry that you have been studying, so that you can be successful with this analysis, I'm not letting you do it. Do you realize I'm acting as your benefactor? I don't want you to do this until you know how to do it, so you can be successful. Because if you don't know what you're doing when you do it, you're likely to blunder it up and get a horrible grade. And these unknowns count a lot, point-wise, in 46L, don't they? I've had students tell me on evaluation, 46L would be a great course if you didn't have unknowns. That's wonderful. That's like saying chemistry would be great if you didn't expect me to understand it. What the hell kind of stuff is this? I'd be a great baseball player, except I can't hit and I can't pitch and I can't field. But I still want to play. Sorry, buddy. You're out. We don't operate that way. You've got to be capable of achieving. And if you haven't recognized that, then you haven't recognized what the heck education is about. Well, that's enough of that preachment. Let's do something else. Let's go back to the question I asked. You got this solution. You got sodium ion in it and ammonium ion in it. What do you do to find out it's got K plus in it? They all look mute.
You have to evaporate the ammonium. And then
You don't evaporate ammonium ion from a water solution. What do you add base? The polynitrite precipitation test is a pH sensitive test. So I don't want to add any base. What do? You said the right word, but you didn't apply it to the right stuff. Remember the word you said, evaporate? Add heat to this solution. What am I going to remove? I will not. What am I going to remove? Water. When you add heat to a system, you will remove the most volatile component. Hey, come on. That's nothing fancy about that. And the most volatile component of this water solution system is water itself. So you carefully evaporate the water until you have a dry residue remaining. Now what do? What do you do now? You transfer the dry residue to a crucible and you do what? You heat it. All right, I'll get out a match. Match is struck. I heated it. I took away the match. You told me to heat it, I heated it. If you're not exactly particular, right on the nose with these directions, I flunk you. That's the way I am. Because I want you to succeed. Remember, if you become the business manager and you give poor directions to one of the persons that works for you and they screw up the whole procedure and cost the company millions of bucks because of that, who do you think is going to get canned? The person who followed your crummy directions or you? You know the answer to that. You! Unless you got some politically corrupt organization for which you work. Then you'll probably blame it on the flunky. But we're assuming we're operating in an honest fashion, which means you are out. You got this residue because you evaporated the water salt. You transfer the residue to a crucible. And now you apply heat to the crucible with your Bunsen flame until? Until what?
Stop smoking.
Until the smoking ceases. What is the smoke?
the gas, ammonia gas.
What is the smoke? When you see the smoke, if I ask you to define a smoke, what will you tell me? Is a smoke a single-phase system? Is it a two-phase system? Is it a three-phase system? You did this stuff in 2045. Let's put it to use. What is a smoke? Don't tell me cigarette. What is a smoke? You've seen plenty of smokes. What is a smoke? Is it a gas alone? It is like hell. What is it? What is a smoke? It's a finely divided particulate solid suspension in vapor. That's a smoke. That's why smoke is not transparent to light, because you got these solid particulates in there. So when you see this smoke above this crucible that contained ammonium ion, I want to know what the smoke is. You all did this work. It's in the laboratory manual. Did you not learn this? Watch out, I'll look up every TA for you folks and say, they can't tell me what the smoke is, so I want no credit issued for assignment 2. How about that? You say, that Horvath is a son of a bitch. You're damn right. Because I want you to learn. What's the smoke? I told you it's a solid. What is the smoke? What are you driving from this crucible if what you remove from the crucible by heating is ammonium ion and chloride ion? What are you driving from the crucible? Ammonia and HCl. That's what you're driving from the crucible, because the strong heating forces H plus transfer from ammonium ion to chloride ion. So from the crucible leaves the colorless gases ammonia and HCl. But as they leave the crucible, they cool off. Not only do they cool off, they bump into each other. What does ammonia and HCl form when they bump into each other? What is it? And that's the smoke. How about that? It's the reformation of ammonium chloride. Okay? And now after the smoke ceases, you can rest assured that all ammonium ion was removed from the original sample, and now you can reconstitute solution by adding a few drops of water, and now you can do the cobalt nitride test successfully for potassium ion. And if you don't go through all of that, you don't know how to do it. It takes a lot shorter time in the lab to do it than it does for me to stand here and preach about it. But I hope you now know what the heck's going on with this investigation. This is what chemistry is about. You have to pay attention to detail. You have to pay attention to how the species and substances which constitute your system behave. Because they don't give a damn what you think or what you wish or what you hope or pray for. They don't care. And they will never react in accord with such behavior on your part. They will only react in accord with your doing chemistry on them. And you better do the right chemistry in order to get the answer which you seek. Ha ha! All right, on we go. All that about reminding you that you are familiar with the development of precipitates in 46L. That's what chapter 19 is about. You think chapter 19 relates to your work in 46L? Shall I repeat the sermon? Now then, you have any familiarity with this stuff? Principal ingredient in teacher's favorite weapon. Is that stuff particularly soluble in water? You find any of that stuff in contact with ocean water? Do you know that that stuff, calcium carbonate, is the principal component of common crustacean shells? You familiar with scallops? Oysters? Tell me, is there a lot of water in the ocean? How about the Pacific Ocean? A lot of water there? All this water, and yet these shells remain intact. How about eggshells? They're principally this stuff too. Have you ever cooked an egg by hard boiling? Did you see the shell dissolve? Well, this tells you that calcium carbonate is not particularly soluble in water, doesn't it? I mean, after all, if calcium carbonate was particularly soluble in water, look at all these embarrassed oysters and scallops you'd have. Oh, my shell dissolved. Oh, how about that? But that doesn't happen, does it? Here's an investigation you can do. Might take a while, but you can do it. Take a little bit of crushed chalk, put it in water, get a straw. Put the straw in the water, keep passing your breath through the water. Eventually you'll see the calcium carbonate dissolve. Because your breath is a good source of CO2. And CO2 in combination with water makes this stuff. And this stuff's acidic, isn't it? We already learned about that stuff. So we're investigating the equilibrium establishable by treating this with this to cause this to dissolve by putting this ion and creating this ion as solution species. Putting that ion in solution and creating that ion. You looked at this yesterday in discussion class. Here's K. Here's the equilibrium constant, because one of the most important things you were looking at yesterday in discussion class is when I have an equilibrium expression, which requires that I have the equilibrium constant value if I'm going to do quantitative analysis on this equilibrium system. How do I get the value for the equilibrium constant if it's not given to me? And what do? You apply something you learned about in Chemistry 2045. That's all you do. What is it that you apply that you learned about in 2045? Anybody know? It's called Hess's Law. Remember that? Do you remember hearing about Hess's Law in 2045? Well, Hess's Law takes advantage of the fact that thermodynamic properties of systems are state functions. Remember that? That means they're independent of the path by which the process in question proceeds. So if I have the standard change in enthalpy for reaction A and the standard change in enthalpy for reaction B, and I add algebraically reaction A to reaction B, then the standard change in enthalpy for the remaining, the added reaction, call it reaction C if you want, is the sum of the standard change in enthalpies for A and B. So what this is about, really, even though we've not yet paid attention to this relationship, I'll write it down, but you're not responsible for this relationship just now. Is that the equilibrium constant for a reaction, specifically the log of the equilibrium constant for the reaction, multiplied times minus 2.3 times R. You know what R is, don't you? Ideal gas constant in common energy units of joules times the temperature in Kelvin times the log of K is equal to the change in standard free energy for the reaction. So if we apply Hess's law to the standard free energies for a combination of reactions, we can get K for this reaction. And that's what this was all about yesterday. You look at this reaction, you let it talk to you. Because when you look at this reaction and we don't give you the K value for it, then you're obligated to get the K value if you're going to do some calculations on this system. And you look at this reaction and see, aha, calcium carbonate's on the left. So what property of calcium carbonate do you need to consider in evaluating K for this reaction? It's solubility product constant, the new equilibrium constant that you learn about at the start of chapter 19. And you've already heard about this in 2045, my bet is, because I'll bet most, if not all of you, are already in assignment 3. And if you're in assignment 3 in the lab, how many of you are in assignment 3 in the lab? At least that far. Now I'll ask the dirty question. Before you did work in assignment 3, did you read the discussion in the lab manual that is preliminary to assignment 3? Good. They do know about this, at least to some extent. Applaud you who did read this stuff. And you know what I'll say to those of you who didn't read it, if you're doing work in assignment 3. But I'll hold my tongue. Mr. Machin might be listening. He might not like the language that I would use. Okay? So, KSP for this stuff. That's going to be a part of this K calculation. And I see this on the left. Well, what do I know about this? The Bronsted-Lowry weak acid that we've considered many times. So I'm going to look for Ka for this thing in the numerator of this expression. Because remember, Ka is for the acid reacting with water, becoming hydronium ion and whatever, conjugate base. So if the acid's on the left, I'm going to have Ka for this stuff in the numerator. If the salt's on the left, I'm going to have KSP for this equilibrium constant in the numerator. Because that's the way KSP is defined. Salt on the left and equilibrium with component ions on the right. And I see bicarb on the right as a product. So I'm not surprised to find out ultimately that if I need a K property for bicarb to evaluate K for this reaction, this K property for bicarb will be in the denominator, because that's on the right. And it winds up being this. You did this yesterday. There's the value. So what does this value mean? Well, it means that calcium carbonate is not readily dissolved by treatment with H2CO3, because this is a damn small number, isn't it? Thermodynamically, this number also means that the net thermodynamic stability of these reactants far exceed the net thermodynamic stability of those products. So put another way, if you go to the laboratory with a solution that's got calcium ion in it, and you treat this solution with sodium bicarb solution, you've added bicarb to the solution, what do you think might happen? Solution contains calcium ion, you add hydrogen carbonate ion. What do you think will happen? What do you think will happen? What is K for this reaction in the opposite direction? What is it? How do I get K for this reaction in the opposite direction? I take the inverse of that, don't I? 1 over 5.4 times 10 to the minus 5 is K for that reaction in the opposite direction. That's a big number. Thermodynamically, that's screaming at me then. If I mix up calcium ion with bicarb ion, I will expect to form a precipitate. The precipitate has a name. What's the name of this precipitate? Calcium carbonate, isn't it? And if I'm looking carefully, I may even observe some bubbles coming out of the system. Right? If you go home and take some tap water, because Florida tap water is usually rich in cations, which react with bicarb to make precipitate. Calcium ion, magnesium ion, iron plus 2, those are common components of Florida tap water. They don't hurt you too much. I've been drinking it for over 40 years. I'm still here. I came here in 67. 67. I like it. That's my state. If you go home, take some tap water, put a little bit of Arm & Hammer sodium bicarb in there, okay? Mix it up. Put it on the stove. Heat it gently. You'll see a precipitate develop, a metal carbonate. And you'll also see the evolution of bones. CO2 bones. You can do this at home. Now then, even though this K value is quite small, can I dissolve calcium carbonate by this method? Is it possible to dissolve calcium carbonate by treating it with this stuff, human breath, applied to a slurry of calcium carbonate and water, and I get the calcium carbonate to dissolve? Yes or no? Can I overwhelm the calcium carbonate? If I only got a little bit of calcium carbonate to dissolve, and I blow my breath through this slurry for 2 hours, you think I'll finally gang up on the calcium carbonate to the extent that the calcium carbonate will dissolve? Yes, I will. This is not an effective way to dissolve calcium carbonate, but it can be done by the gang up factor. Did you read about the gang up factor in chapter 18 in our notes? Well then, you heard about this. Hey, you know your job is to read this stuff. Pay attention to it. And we correspondingly discuss it as necessary in our gathering here. Now then, many of you also looked at this. But I want to try to be sure that you have a good handle on how to develop a sense of smell. How to learn how to evaluate Ks for which the K value is not given. And what do you have to do? You have to look at the equilibrium reaction in which you're interested and figure out of what fundamental K values is this thing composed. Now, what fundamental K values have we talked about so far? Well, the first one was Kw. And after Kw came Ka. And after Ka came Kb. And that's all we looked at through chapter 18. Now we got to chapter 19. What's the new type of K value you looked at? KSP. That's it. So far, all the equilibrium reactions for which you have to evaluate K will be a composite in some fashion of Kas and or Kbs and or KSPs and possibly KW. And when we get to the end of this chapter, you'll find out we're going to add a new K called K sub F, where the F means formation. Formation specifically of complex ions. But we'll wait on that one till the end of chapter 19. Now let's look at this transformation. Silver chloride. You know that this isn't a very soluble material. And you also know by way of your introductory considerations for chapter 19 that calculating the solubility for silver chloride is a very simple task. Why is that true? Why is calculating the solubility for a salt like silver chloride a very simple task? Why? Answer: the solubility for a salt like silver chloride may be calculated correctly from its KSP value alone. No other K is necessary to be considered. Why is that true?
Because neither of them affect pH.
Because neither component ion of silver chloride exert any effect to speak of on solution pH. Which means when silver ion and chloride ion are put into solution by dissolving silver chloride, silver ion doesn't go someplace else because of acid-base chemistry, neither does chloride ion. Now you know that for sure about chloride ion, because it's the conjugate base of a strong acid, specifically HCl. And if you didn't know that about silver ion, you go to the laboratory, take a solution that's rich in silver ion and contains an anion which has no ability to affect pH. And the only common salt of silver ion which is quite soluble in water is silver nitrate. So you go to the laboratory, get some silver nitrate solution. Say 10th molar. The one you got in the laboratory is 200th molar. That's good enough. Because you know nitrate ion is, like chloride ion, a conjugate base of strong acid, right? So the presence of nitrate ion exerts no impact on solution pH. So observe the pH of silver. You observe the pH by indicator analysis, what have you, for silver nitrate solution. And if you see the pH is the same as the deionized water solvent itself, you know that silver ion is not showing any impact on pH. And that's it. And that's what you'd find out. So you'd say, ha, this stuff, silver chloride, I can calculate its solubility correctly from its KSP. Silver chloride in equilibrium with silver ion aqueous and chloride ion aqueous. So the solubility will be equal to the molarity, equilibrium molarity of silver ion. The solubility will also be equal to the equilibrium molarity of chloride ion for that equilibrium as written. And the square root of KSP will give you the solubility. You did this yesterday. Ha ha! But that easy game is over when you get to calcium carbonate. Why is that easy game over when you get to calcium carbonate? Now, hydrated calcium ion is a very, very weak Bronsted acid, so we can neglect its Bronsted acidity. But not true for the basicity of carbonate ion. You see carbonate ion in our acid-base table, don't you? So now the situation gets more complicated. When for a semi-soluble salt, we have a component ion, usually the anion, which is a Bronsted base of sufficient strength to react measurably with water and make the pH go up for the system because of the production of hydroxide ion. So when you want to go about the business of calculating solubility for a material of like calcium carbonate, beside KSP, you also need what equilibrium constant consideration? Kb carbonate ion. So the situation is getting more complicated. Now then, forget that for the moment. Let's go back to this. I want to calculate K for this equilibrium. It's telling me I'm going to have KSP for silver chloride on the left to what power? To what power? Squared. Uh-oh. What do I expect to find H2S in this evaluation process of the equilibrium constant? What property of H2S? Is the H2S not a weak acid? See it on our acid-base table? So would you be surprised to find that evaluation of equilibrium constant for this system involves Ka for H2S? Wouldn't be surprised to find that out either, would you? And we go over here, we see silver sulfide. Now maybe as yet you have no knowledge of silver sulfide. So you get out our information sheet. Get it out. Let's go. You see silver sulfide on this information sheet? What does the KSP for silver sulfide suggest about the water solubility of silver sulfide? Damn slightly soluble. Boy, that stuff is a stable stuff. Now bear in mind, and this is in the notes, I hope you read about it, and we're going to say more about this. Solubilities and KSPs are not the same thing. And KSP is not a direct measure of solubility. Never. Unless you have a salt like silver chloride, where you can get the S value, the solubility, from the KSP alone. In that instance, you can take KSP as a measure of solubility, but it's still not the solubility. But for material like calcium carbonate, forget it. KSP is not a measure of its solubility. When we go back and look at this, and I see Ag2S on the right, my information sheet has told me that it's not very soluble in water, so I expect to find an evaluating K for this thing. KSP for silver sulfide. Do I expect to find this KSP value in the numerator or denominator of the evaluation process? Numerator or denominator? KSP is on the right. Remember how KSP is defined? Salt on the left. Salt is the reactant. Double arrows. Component ions on the right. This silver sulfide's on the right. Do I expect to find KSP for silver sulfide as I evaluate K for this equilibrium? Do I expect to find KSP to appear in the numerator or denominator? Denominator. Silver chloride, numerator. Quantity squared. We're learning to let that thing talk to us. We're learning to let that equilibrium reaction tell us the K's of which it is composed. Now then, next information. Here's the KSP expression for silver sulfide. Because when I dissolve silver sulfide in water, this reaction takes place. And not only does this reaction take place, for every mole of sulfide ion which goes in solution, how much of the sulfide ion converts to products hydroxide ion and HS minus? How much of the sulfide ion converts? Remember where sulfide ion is on our acid-base table? Take a look. Is it not found to be a stronger base than hydroxide ion? And we've already recognized the solubility of silver sulfide is damn small. So the amount of sulfide ion we're going to put in solution ain't much. So its M sub I value is damn small, isn't it? So here's a base which is stronger than hydroxide ion, and we're putting in the solution at an initial molarity which is damn small. To what extent will it convert to HS minus and hydroxide ion? 100%, you betcha. So watch out for these stupid damn textbooks who will try to foist upon you the incorrect statement that the KSP for a material like silver sulfide is this. How can I have a KSP depending on a molarity which is not there? Zero. What kind of equilibrium, what kind of equation is this? The value of this is zero. This can never be an equality. More complications. Oh, because of chemistry, not because of Horvath. It's chemistry. That's what's tough. Not me. I just got my mind made up that I'm going to show you what chemistry's like. So, here's the KSP expression. All it requires to write a KSP expression is to pay attention to the chemistry which the semi-soluble salt in question shows us when it dissolves in water. That's all you got to do. Silver chloride, neither the component ions react with water. So silver chloride in equilibrium with silver ion and chloride ion. So before we go further with this, let's jump over to this. You see KSP for calcium carbonate? So to our first glance is going to say, well, when calcium carbonate dissociates in water, it puts calcium ion and carbonate ion in water. Here's the question. We're not going to answer the question right now, but here's the question. Can I write the KSP for calcium carbonate a different way? Keep that in mind. Back to this. We've reminded ourselves about the K's of which this thing is composed. So I'm looking at this equilibrium constant expression, and I now have to ask myself, how do I introduce these K's into this equilibrium constant expression so I can get on with calculating K? Well, let's try this first. Because I looked at this, I said, I'm going to have KSP for silver chloride to the second power in this evaluation process for K. So I multiply by silver ion molarity, top and bottom squared. There's multiplication by 1. But what has it achieved? Do I now not have KSP silver chloride quantity squared? Yep, there it is. Okay, so there's KSP silver chloride quantity squared. All right? Now then, here's H2S denominator. Here's hydronium ion numerator. So let me go over here and write HS minus molarity, top and bottom. Multiplication by 1 again. Why did I do that? Now I got H2S denominator, hydronium ion. Let's take out the second power and turn it into first power. Hydronium ion molarity numerator times HS molarity numerator. What's that give me? KaH2S, doesn't it? Well now, what have I not yet paid attention to? I've not yet paid attention to my silver sulfide KSP, which I know has got to be in the denominator of this thing. And here's the KSP thing. So I need this, don't I? Okay? And now I say silver ion squared times HS minus times hydroxide ion. What's that give me? KSP silver sulfide denominator. Alright? So I've accounted for molarity chloride ion squared times molarity silver ion squared. That's KSP silver chloride squared. I've accounted for H2S denominator, hydronium ion HS minus, that's KaH2S. And I've accounted for KSP silver sulfide in the denominator. So I go back and re-examine what I got. Okay? And what do I see remaining? I see hydronium ion first power times this hydroxide ion, don't I? That's all I see remaining. And I search through my memory banks and I say, for an equilibrium system, what the heck is the hydronium ion molarity times the hydroxide ion molarity? And I say, it's Kw, don't I? And there it is. So I put in Kw, numerator, I put in the numbers, and crank. Pick it up from this point next time.